Hi everyone, welcome back to Data Cadence. My name is Rahul and I work as a senior applied research scientist. And in today's video, we are going to dive deep into one of the most renowned and effective models for object detection, that is YOLO, or you look only once. And YOLO has revolutionized the field with its remarkable ability to detect and classify objects in real time, making it a top choice for many of the projects. But to truly harness the power of YOLO, it's crucial to understand what's happening under the hood. So in this video, we will explore the internal workings of YOLO's loss function, a key component that drives its performance, and why this is important. If you have ever worked with YOLO or you plan to, knowing the intricacies of its loss function isn't just beneficial, it's essential. Moreover, this knowledge is vital from an interview perspective. So employers value candidates who can explain the underlying mechanics of the models that they have used, and demonstrating a thorough understanding and capability in their field definitely helps. So without further ado, let's begin. So YOLO is one of the most popular object detections model that exists out there, and it aims to simultaneously predict multiple aspects of objects within an image using a simple neural network. And the main thing here that we need to understand is that there are certain key tasks that are associated when it comes to YOLO. So the first one is the bounding box regression, and for that we will utilize something known to us as localization loss. The second one is objectness scoring. For this we will utilize the confidence loss. The third task is the classification, for which we will look at the classification loss. And then the overall loss function in YOLO is a combination of these losses that I just mentioned, right? So the loss function is designed to optimize these tasks simultaneously because there is a lot going under the hood. So let's have a look at each of these tasks in detail and try to understand the individual loss functions and how we can combine all of these loss towards the end to arrive at the finalized and the overall loss function for YOLO. So the first task, like we mentioned, is bounding box regression. So the objective here is to predict the accurate bounding boxes around the detected objects, and YOLO predicts the coordinates for the center of the bounding box. Let's call that coordinate to be say x comma y, and the width of that particular thing and the height of that particular thing. Let's call them w and h respectively. And the goal here is to minimize the error between the predicted bounding box and the ground truth. That's obvious. And that's why it's also known as bounding box regression. And the localization loss looks something like this. So you have lambda 1 times the summation of all the bounding boxes that you have, and then you have a mean squared error for each of these things, that is x, y, w and h. And xi is what you have as the ground truth, and xi star is what you predict, or whatever comes out of the YOLO model as the prediction for that particular bounding box. And similarly, you repeat this thing for xy, that is the coordinates of the center of the bounding box, and the width and the height, that is w and h. And this is pretty intuitive and straightforward. And lambda 1 is basically the scaling factor or the weight that you want to assign to your localization loss, or the loss corresponding to your bounding box regression. And often these lambda 1, lambda 2 and whatever you see are just like weights, however much weightage you want to give to each of these objectives or each of these tasks, and the loss function corresponding to those. So this is pretty intuitive and it's pretty clear. And MSE is obviously mean squared error. So I've just written is as MSE, but I'm sure that you're aware about what a mean squared error is. So let's talk about the second key task, that is objectness scoring. So the objective here is to determine the likelihood that a bounding box contains an object, and YOLO predicts POBJ, that is the objectness score, and this is done for each of the bounding box that YOLO predicts. And what this reflects is both the presence of an object and the confidence in the bounding box's accuracy as well. So that's what you have it as POBJ. And talking about the mathematical formulation, so here under this particular task, you have two types of losses. That is, first one is the presence loss, which is the loss function corresponding to presence of a particular object in a predicted bounding box. And the second one is the no object loss, which is the loss function corresponding to no object being present in the corresponding bounding box. So again, it's pretty straightforward. The loss of presence could be given as lambda 2. Again, lambda 2 is the weighing or the weightage that you want to give to the presence loss. And the loss presence is given as lambda 2 times the summation overall of your losses for the POBJ and the POBJ star. And POBJ, like we mentioned, is the model's predicted probability that a bounding box contains an object. And POBJ star is the true binary label indicating whether a bounding box actually contains an object or not. And BC, like you all know again, is simply binary cross entropy. So that's pretty intuitive. And for the no object loss, the p obj star simply becomes 0. And again, that's pretty straightforward. And lambda 3 is the weightage that you want to give to the no object loss. Finally, let's talk about the final task, that is classification. And the objective here is to predict the class of the object within each of the bounding box. So in the first two tasks, you identify the bounding box and whether an object lies in that particular bounding box or not. And if at all an object lies within that particular bounding box, what is the class that this particular object belongs to? So that is exactly what we are doing in classification. And YOLO predicts class probabilities for each of the bounding boxes to check which of the classes does this particular object lie to or belong to, right? So the classification loss is computed to ensure that predicted class probabilities match your ground truth labels. And this is how the classification loss is then defined. The loss classification is simply given as lambda 4 times the summation over all of your bounding boxes of the categorical class entropy for your probability of your original class and the predicted probability of your particular class. And CC, like I mentioned, is simply categorical cross entropy in this particular case. And this is pretty straightforward. Once you have all of these individual tasks and the loss functions corresponding to those, you can define a combined loss of the YOLO, that is loss for the localization plus loss for the presence plus loss for the no object and the loss for the classification. You can simply add these four to have a overall loss function for your YOLO. And this particular overall loss ensures that the model accurately learns to localize the object, that is bounding box regression, to assess the presence of object, that is objectness scoring, and finally to classify the object types, that is classification. So it's intuitive and pretty straightforward. So we have just explored the inner workings of YOLO's loss function, dissecting the details that make this powerful model tick. And while diving into the specifics of the bounding box regression, objectness scoring, and classification might seem complex, but we have broken it down to make it straightforward and accessible. Understanding these details is more than just an academic exercise for anyone working with YOLO in real world projects or preparing for data science interviews. Knowing how YOLO's loss function operates provides a significant advantage. It not only equips you to optimize and troubleshoot the model effectively, but also showcases your depth of knowledge to potential employers. So hopefully this video helped you. Don't forget to like, subscribe, and hit the notification bell for more in-depth content around data science and machine learning, and also around interview prep. My goal here is to cover multiple aspects within data science, be it NLP, classical machine learning, stats, system design, computer vision, and a lot more. So do stay tuned for that, and I will see you in the next video. Then until then, stay safe and keep learning.